Okay, picking back up this rather complicated work and energy problem. With the second part, what we've done in the first part is we've figured out an expression that can be solved quadratically for the displacement of the spring, that is the compression distance of the spring as our crate comes to rest. For the second part, I'm asked to determine how far up the ramp the block travels when the spring relaunches it. So here's the situation. The block will come down, compress the spring will then relaunch it and it'll move back up the ramp. So first let's ask ourselves, what do we expect? It's always a good thing to ask yourselves in a physics problem. If you're thinking through it physically, ask what you expect to happen. Well, I know I've got friction involved, and friction is going to bleed energy out of my system. And so I do not expect the block to go as high as it did. In other words, the vertical distance, if I started here, I'm going to end up somewhere here, because the energy that it would take to get back up to my original position, I've lost due to friction. Well, if my height's lower, then the distance it's going to travel up the ramp, which is what I'm asked to find, is also going to be lower. So I've indicated that here. H final, which is where the block ends up after this whole process, is going to be less than H, the original height. So let's see how that works out. We'll see that really well with the numbers. We'll see how it works out here. Now, in this portion of the problem, I'm going to solve it in one step instead of two. You could have solved the first one in one step if you so desired. I'm just going to account for everything and let the chips fall where they may. So this is my energy equation. This is potential energy spring initial plus potential energy gravitational initial plus initial kinetic energy plus the work from non-conservative forces, in this case just friction, which is also going to be a loss, right? This term I'm adding the term, but inside that is going to be buried a negative sign because friction represents a loss in energy. Final kinetic energy and final gravitational potential energy. Notice I'm starting when the block is at rest, I'm ending when the block is at rest, so my kinetic energy terms go away. So let me unpack that. Initial spring potential is 1/2 k delta x squared, right? I solved for delta x in the previous portion. The gravitational potential energy, remember I've set my 0 point at the uncompressed length of the spring, so my initial gravitational potential energy will be negative because my block is below that position. So we've got minus mg delta x sine theta plus 0 for no kinetic energy, and then my dissipative force is mu k mg cosine theta, that's the frictional force, times this distance. So this is what's changed since I'm solving it in one step. Before I calculated the friction due to the distance down the ramp, and now I'm calculating it due to the distance up the ramp and the compression distance of the spring. I did this in 2 steps earlier. There should be a subscript of d final here, right? This is not the same d that I came down the ramp with. I'm going back up it. And that's got to be equal to the final potential energy, which is just mgh final. So what I'm going to do here is divide through by mg to clean this up a little bit. What I get here is the final height is equal to this stuff, k over 2 gm delta x squared minus delta x sine theta minus mu k cosine theta. This parentheses terms d plus delta x again, that should be d final. And this tells me my final height. That's not exactly what I'm asked for. I'm asked for the final distance up the ramp, so I need to change that into a d, which I can do by noting that from the trig, d final is equal to h final over sine theta. D is going to be the hypotenuse. If you can't remember where that comes from over here. D is the hypotenuse, h is the opposite side of the angle theta. If you solve that trig function, you get df. So df is equal to hf sine theta, where hf is given by this expression. Alright, so this is a reasonably complicated problem. In fact, if you are in my class, I'm making this video specifically for a Physics 1500 class. If you're in my class, this is liable to be the most complicated problem you will see all semester. This is pretty difficult, I won't lie. My strategy as always, though, is if you can understand the difficult problems, the problems that aren't so difficult will be easier to understand. So as you're working through this, I would encourage you to work it through 2 or 3 times from beginning to end. Not just to copy the steps, not to just to memorize the sequence of what we do, but to understand where these terms come from, understand why they appear where they do. Alright, in the next video we'll put some numbers to it and solve it.